All right, ladies and gentlemen, we are going to wrap up this kinetics chapter today, and I actually really like how this chapter is broken down and how we have split this chapter into 3 sections. We're doing the third part of it today, okay? So kinetics is all about the speeds of reactions, and if you really think about it, the first day that we were in this chapter and the second day of this chapter, we essentially had the same goal, whether you realize it or not. Both days, our primary goal was coming up with or determining a rate law for something, for a reaction, for a particular reactant, and we saw different methods to do that. So if you go back and you look at your notes from the beginning of this chapter, the first day, we determined rate laws by looking at a table of data and doing those, I call them compare line by line kind of problems, like from this line to this line, the molarity is multiplied by 2. From this line to this line, the rate is multiplied by 4. And we used that kind of data to figure out the exponent. Second day in this chapter, we focused on figuring out that exponent, the order, by looking at graphs. Okay, and you didn't have to come up with the graphs on your own. They were given to you, and what you were looking for is which kind of a plot on a graph gives me the straight line, the linear data. And that's how we determine the rate law. Our goal is the same today. We're going to find a further way, a third way to find a rate law using a different method. Okay? And we're going to learn a little bit of vocabulary before we really get into how do you find that rate law. And what we're going to look at today gets into something we have looked at before. Do you all remember back in the fall, we did some problems called Hess's law problems? Remember you had like multiple equations and you had to rearrange them so that they would add together to equal what you wanted. Do you remember those? Okay. I'm not sure if I used this term or not, okay, reaction mechanism, but here's the deal. Here's the take-home message. Okay, the overarching thing here. Most reactions that you observe in the lab, out in nature, do not happen in just one step. Most reactions in our world occur in more than one step, maybe 2 steps, maybe 3, maybe 5, 15, whatever. This collection of steps is called a reaction mechanism, okay? It's a series of steps by which some chemical reaction occurs. Okay, so when we did those Hess's law problems and you were presented with 4 equations that you needed to rearrange to add to equal one final one, you were looking at what's called a reaction mechanism. Okay? And you can write this down if you want, but you might want to hold off until we have an example in front of us. Okay? Let me show you what an example of a reaction mechanism would look like. Okay? It might look something like this. These 2 equations together make up a reaction mechanism. And here's another vocabulary term that I used before, so you should have heard it. These individual steps, guys, are called elementary steps. Okay, I don't know if you remember that or not. But this mechanism contains 2 elementary steps. Some mechanisms will have 3, 4, 5. Okay? And just like we did with those Hess's law problems, we're going to be adding these elementary steps together. Okay? Do you remember from those Hess's law problems that you can cancel things out? If something appears in identical form on opposite sides of the arrow, you can get rid of it. You can cancel it out. Look at this mechanism. Do you see something that I can cancel out? All right, one of the NO2s, yeah, okay. Do you see anything else? Yeah, the NO3 I can get rid of as well. Right? And then if you added everything together, whatever's left, do you agree that I would end up with this? Yeah. Okay. So these are elementary steps. This I would call an overall reaction. And the point here, that statement on the previous slide, guys, the point is when you look at an overall reaction, that's just, it's like a summary of what happened. It's not telling you the play-by-play of what actually occurred. And just in case you're worried about this, would I expect you to look at an overall reaction and just say, oh yeah, I can clearly see that that took place in 2 elementary steps and here's what they are? No, I wouldn't expect you to know that. This would have to be given to you. Okay? Now, these things that I crossed out, guys, they have names. And I don't mean chemical names. There's a little bit more vocabulary here. This NO3 that got canceled out, ladies and gentlemen, this is an example of an intermediate. Okay, that's a vocabulary word you need to know. It's an intermediate. Intermediates are things that get canceled out, but they have a more specific definition than that because, for example, this is not an intermediate. This is something else, which I'll get to in a second. In order to qualify as an intermediate, it needs to be canceled out, not represented in the overall reaction, but it also must be a product of an elementary step first and a reactant later on. Okay? That might be in the very next step. It might be 1, 2 steps below. But the point is, an intermediate gets canceled out, shows up as a product first, and a reactant later. This doesn't fit that definition. This isn't an intermediate. The NO2, believe it or not, is a catalyst. Okay. Catalysts also get canceled out, but a catalyst has the opposite definition. Catalysts show up as a reactant first, and then somewhere later in that mechanism will pop back out as a product. So catalyst and intermediate have the opposite definitions. And guys, you will have questions both in multiple choice and free response that will be as simple as, here is a mechanism, identify the intermediate. What is the intermediate? Or what in this reaction mechanism is the catalyst? Okay? Simple as that. Alright, so let's just review. We've got a few new terms here. What do you call this set of 2 equations? This whole thing together, what do you call it? Reaction mechanism. What are these individual pieces? Elementary steps. Okay. right, so we talked about intermediates, catalysts, elementary steps. Here is another vocabulary word you need to know, molecularity. And I want you to make a note to yourself. Molecularity is a term that we use when we're talking about elementary steps. Okay? You don't talk about the molecularity of an overall reaction. Okay? And I'll explain this a little bit. You know, this wording is not great. Okay? Molecularity is essentially how many reactants are reacting, and to be even more specific, how many moles are reacting. Okay, so it says the number of species that must collide to produce this reaction. It's basically how many moles of reactant are reacting, and I'll show you what I mean here. There's a chart from our old textbook, and I kept it in here because I really like this chart. Okay, first of all, guys, molecularity. It's a term we use with elementary steps. Okay, don't look at this bottom statement yet. Focus on this chart. Molecularity, how many pieces of your reactant are reacting? So look at this line right here. Do you guys agree that this reaction has one reactant? Do you agree? Okay, so I would call this elementary step unimolecular. That prefix uni means one. Okay, unimolecular. All right, now look at the second line. Yes, this only has one reactant, but guys, it has a coefficient of 2. It's got 2 moles reacting. I'm not going to call this a unimolecular, I'm going to call it a bimolecular reaction, or a bimolecular elementary step. Okay, this one is also bimolecular. When you start getting to 3 or more, right, we don't get specific, we don't go into the tri, tetra, pent, and all that. The prefix ter, T-E-R, means 3 or more. Okay, if you have 3 or more pieces reacting in an elementary step, you say that that elementary step is termolecular. Okay. Now, next to this statement, I want you to put a big star and circle the word only. Because let's look at what else is in this chart. We have these elementary steps, they're telling us the molecularity, and then over here they've got rate laws. What's on that column on the far right, those are the rate laws for each of these elementary steps. There is something you can do with elementary steps that you can't do with any other kind of reaction. If you will notice what they have done, look at this example right here, 2A plus B. They have taken the coefficients from these elementary steps, and the coefficients became the exponents in that rate law. Okay, the coefficients from these elementary steps became the coefficients in the rate law. Now, I want you just to kind of stop for a second. Realize we have never done that so far in this chapter. Think about what we have done to figure out those exponents. We either examined a chart of data, compared lines, or we looked at graphs. Guys, nowhere in this chapter have we focused on the coefficients. In fact, until today, we haven't even really said, check to see if these reactions were even balanced. We didn't care, because we didn't need the coefficients. Well, if you're dealing with an elementary step, then you can. That's permitted, but only for elementary steps. Now, there's two things that you might be wondering right now. Number one, you might be wondering, how am I going to know if a reaction is an elementary step? How do I know it's not an overall reaction? Well, they're going to tell you. They're either going to say, the following elementary step, comma, or maybe it's a reaction that is within a reaction mechanism. That would make it an elementary step. The second thing you might be wondering is, okay, that's great. That's fantastic that you can do this. You can write the rate laws using the coefficients. That's all fine and good, but who cares? You can only do that for an elementary step. I mean, don't we want the rate law for the whole reaction? Hold that thought. All right? I'm going to give you an analogy. Okay? I want you to imagine that you and 4 of your friends have decided that you're going to run a marathon together. Good for you. That's a lot of training and a lot of time. Good for you. Okay, go get them. And you and your 4 friends, not only are you going to run this race together, but you have made a pact that when you run this race, the 5 of you are going to stay together no matter what. Because you're very close and you're very good friends and you're very loyal to one another. Okay? If you're going to make that deal that the 5 of you are going to stay together, which person in your group decides how fast you move through the race? The slowest person. You're absolutely right. That is the person that's going to determine how fast you move through this race. Let's bring it back to chemistry. Okay? If we're dealing with a reaction mechanism, a multi-step reaction, one of those elementary steps is going to be the slowest one. They're not going to operate at the same speed. And that slowest step is going to determine the speed, the rate of the whole overall reaction. Okay? So that, what we call the slow step, we call it the rate determining step because it determines the rate of the entire reaction. Okay? So let's look at another mechanism. Let's look at this one. Okay? It's a mechanism that has 2 elementary steps. And ultimately, we're going to be adding these 2 together. Let's review a little bit. Does this mechanism, does it have an intermediate? Yes or no? If you need to review what an intermediate is, please do. Okay, what is the intermediate? F or F2? Which one? F. Just regular old F. You got it. Does this mechanism have a catalyst? No, it doesn't. And some mechanisms don't have a catalyst. That's okay. It does have an intermediate, though. Okay? And look at the information we've been given. We've been given information about how fast these steps are. And they're telling us that this is the slow step. Okay? This is the slow runner in my group of runners. Okay, well, let me ask you something before we get to this question here. What is something, 2 slides back, or maybe 3, what is something that you can do for elementary steps that you cannot do for any other kind of reaction? Use the coefficients and turn them into the exponents, okay? Fine. Tell me, please, use this elementary step. Can you all tell me what would the rate law for this elementary step look like? Tell me what I would write. Well, rate. Okay, rate equals what? K times what? All right, NO2 to what power? Why to the first power? How'd you know that? It has a coefficient of 1. Okay, what else? F times F2 to what power? To the first power. Again, because it has a coefficient of 1. All right, great. And again, I know what you're thinking. Well, that's the rate law for that elementary step, but they want the rate law for the whole thing. Well, let me say something to you, and you might want to hold on to something because it's kind of earth-shattering. Okay, maybe not. I might be overselling it just a tad. Are you ready? I'll say it twice. The rate law for the slow step, the rate law for your rate determining elementary step is the rate law for the whole thing. What? I know. I'm amazed too. I know. All right, let me say it again. The rate law found from your slow rate determining elementary step is also the rate law for the entire overall reaction. Okay, so determine the rate law, check, done. We didn't have to use a graph, we didn't have to use a data table. It was that easy. What is the overall balanced equation? Well, let's just add everything. You guys tell me what to write. We canceled out the F, what's left? All right, 2NO2, what else? F2. Plus F2 yields?
2NO2.
Very good. Okay. Do these coefficients match the exponents? No, they don't. And that's okay. This is not an elementary step, guys. This is an overall reaction. Coefficients of an overall reaction don't have to match the exponents. Okay, that's all right. So we've just solved this problem. Done. Now, he asked a great question. Will they always give you this information? Absolutely, they have to. You have to know which step is the slow step. And I know what you're thinking. No way are they going to use words like slow, fast. Like, this is AP Chem. Aren't they going to be more technical? Probably not. Okay? They're probably going to use words just like that. The most technical that you could get, maybe they don't use words like this. Maybe they give you values for these rate constants. But guys, they're going to make it really obvious. Like, K2 is equal to 4,516, and K1 is equal to 0.12. This is really fast compared to this. Much larger than that. They're telling you this is the slow step. Okay? A small value for K means a slow reaction. All right, let's look at another example. Let's look at this one. Looks really similar. It's got 2 elementary steps. It says, using the following mechanism, and we're supposed to do the exact same thing that we did on the previous slide. And then I say, be careful. Okay, well, why would I say that? What's the intermediate in this equation, or this mechanism? Okay, great. They've given us speed information, fast, slow. Okay, well, if I ask you to do what we did on the previous slide, write the rate law from the slow step, we got a problem here. If you're supposed to write the rate law from this slow step, but we just canceled this out, do I include it? Here's the issue, guys. Okay? on the previous slide, the rate determining step was the first step. And in all honesty, 95% of the problems you come across, the slow step will be the first step. But what if it isn't, and you run into this problem? Here's what you have to do. This won't come up often, but it does come up. You can't, if you're, first of all, let me just make sure we're all clear on this. This is if your slow step isn't first. In this case, it's second, maybe it's third. Okay? If that is the case, you cannot just look at your slow step reactants. You have to look at your slow steps reactants and everything above it. Okay? Because this is where the breakdown is going to happen. So we have to look at all of this. Now look at what I've highlighted in yellow. And look at it all together. Is there anything that I could cancel out from what I've highlighted in yellow? NOBr2, that intermediate. It's gone. Ignore it. If I asked you to look at everything that remains and said, write the rate law from everything that remains, what would your rate law look like? Rate equals K times what? NO squared, because there's two of them, times Br2 to what power? To the first power. Okay. Guys, that's the rate law that I'm dealing with here. Okay? Now the only reason I had to do this was because my slow step wasn't first. Is this going to come up often? No, but it does come up. Okay? So this is my overall rate law for the whole thing. Right? It does not include the intermediate, because intermediates don't influence the rate of a reaction. Okay. Overall balanced equation, now you're looking at everything. Okay? Not just what's highlighted. Here's my overall. 2NO plus bromine yields. Okay? Problem solved. Okay, so let's just kind of recap what we've got here, guys. We now have 3 methods to find a rate law. Compare line by line, look at graphs and see which plot gives us the linear data. And now we have a third method, which is finding a rate law by knowing what is the rate determining step within a reaction mechanism. Okay? How do you know which method to use? Depends on what you're given. Okay? All right. So we're going to change gears here a little bit to wrap up this chapter. Okay, so a lot of what's at the end of this chapter, guys, is stuff that you did in Chem 1. So a lot of it's going to be review. All right? And the take-home message here in the end of this chapter is called the collision model. And we're going to talk about, in this last part, why is it that some reactions are faster than others? What is happening on an atomic molecular level when things react? And the key idea here is that reactions are pretty violent. Okay, it's not like two reactants just la 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 and come over and happen to make contact and, voila, we have products. It's violent. Reactants have to crash into one another. Okay, they have to have collisions. However, only a small percentage of those collisions are actually going to yield products. Why? It's an energy reason. This is review from Chem 1. You should know this term or have heard it before. Right? Activation energy, ladies and gentlemen. Here's a simple definition. Are you ready? It's the energy required to begin a reaction or to get a reaction going. The energy required to get a reaction going. And I'm just going to make up a number. This is a ridiculous number. Let's say a particular reaction has an activation energy of 20 joules. If these two reactant particles crash into each other with 19 joules of energy, that's not going to cut it. They're just going to separate and go back on their merry way. If they crash into each other with 20 joules or more, then we will likely get some product. Okay? We can look at this graphically. Right? We've seen these energy curves many times over this year. Let me just help you get your bearings here, just to refresh your memory. All right, your reactants are always on the far left. Products are always on the far right. Okay, let's just see what you remember. Look at the general shape. Products are below reactants. Ladies and gentlemen, is this an endo or exothermic curve? Exo. Okay. Remember, your endo would look something like that. Okay. And you might be asked to interpret an energy profile. That's what they call these, energy profiles. You might be asked to label certain things on a graph that looks like this, maybe. For example, you might be asked to label the activation energy, and here's what I would draw. Okay, something like that. You'll see capital E with a sub A, that's activation energy. The distance on the y-axis, which is energy, from your original reactants up to the top. Okay, your products are over here. If I was looking at an endothermic curve, here's what activation energy where it would be represented. Okay, from original reactants to the top of the hill. Okay. There's another vocabulary term on here. I'm sorry it's in such small font. Transition state. That's a term you need to know. The transition state, if you look at this molecular model here, it's not the reactants, it's not the products. It's like a hybrid between reactants and products. That's how I think of it. It's sort of the halfway structure between reactants and products. Okay. This is a person's name, by the way. Arrhenius is responsible for the collision theory and everything that goes along with it. Okay. Arrhenius also talked about the relationship of reaction rate and temperature. Now, you guys tell me, if you raise the temperature of anything, solid, liquid, gas, doesn't matter, what happens to the particles? What do? They move faster. Well, what do you think? If things are moving faster, do you think there are going to be more collisions? What do you think? Yeah. And not just more collisions, but more collisions with the appropriate amount of energy. Okay? So the rate should go up as temperature increases. As you raise the temperature, you're going to have more molecules with that required, what was the number I said, 20 joules. Okay? And it's an exponential increase, guys. As temperature goes up, the number of collisions doesn't go up proportionally, linearly. It goes up exponentially. And if you go on to higher levels of chem, there is math associated with this. We're not going to do the math, okay? But there is math where you can say, if I raise the temperature this much, I should get this many more collisions. And I'm just going to make up a number. Let's say you raise the temperature, and this is a ridiculous number, but your math says that you should get 5,000 collisions. Well, when you go into the lab and actually measure that, you're not going to get 5,000. Maybe you only get 4,800 collisions. Your observed rate is going to be less than your math would predict. And here's why. Okay, let's think about what's required. Two reactant particles, they have to collide. They have to collide with the right amount of energy. Guys, there is one more requirement, and it's called molecular orientation. That is a really fancy term that just means the angle at which these reactant particles strike each other. Okay? So imagine my two fists are these reactant particles. Okay? Let's use that number 20 again. 20 joules is required. Here they come. And they're going to collide, and they collide with 21 joules. Is that enough? Yeah. But maybe these two particles striking each other at this angle, maybe that's not going to cut it. Maybe if I rotate this one 90 degrees, now it's going to work. The point is, these reactants need to collide at just the right angle that's going to allow bonds to be formed. Okay? See if you were paying attention. What is that structure called that's between reactants and products? Transition state. Okay? These reactants need to form some new bonds to create that transition state, which will then go on to create product. Okay. So, guys, if you think about it, it is a miracle that reactions happen at all. They have to collide. They have to collide with the right amount of energy. They have to collide at exactly the right angle. It's a miracle reactions happen at all. But they do. Okay? There is an equation that goes with this. You can write it down or not, your choice. It's not on the test, it is not on the AP exam. Okay? This is simply showing the relationship between temperature and the rate constant, which really is saying the relationship between temperature and speed of the reaction. And what is that relationship? Temperature goes up, what happens to the speed? Also goes up. Okay? But we're not going to do the math with this. Okay, now, let me tie these two concepts together that we've been talking about. Collision theory, Arrhenius, and reaction mechanisms. Guys, it should make sense to you that in a reaction mechanism, that slow rate determining step is the slow step because it has the highest activation energy. That should make sense to you. If you have to run over 3 hills, the hill that is the highest, that's going to take you the most amount of time to run over. So the reason the slow step is the slow step is because it has the greatest activation energy. Let me give you a visual way to think about that. Okay. I mean, these graphics, I am really high-tech with this. I mean, this is an energy curve, everybody. I know you're impressed. It's okay. You don't have to tell me. reactants, products. Is this overall curve, ladies and gentlemen, endo or exo? Exo, thank you. Okay, not a trick question, everybody. How many elementary steps are in this mechanism? 3. 1, 2, 3. Okay. 3 elementary steps. Of those 3, which one is the rate determining step? Why the second one? You're right. Thank you for saying that. Thank you for not saying because it's the biggest bump. Okay? If this is a free response question and I asked you that, please don't say because it's the biggest bump or because it's the tallest. It's because it has the greatest activation energy. So yes, this middle elementary step would be our rate determining step. This would be one of those situations where we have to highlight the reactants of that step and the one above it. That would be one of those situations. Okay. Intermediates. Intermediates are things that get crossed out, canceled out of reaction mechanisms, but what's the other part of a definition of an intermediate? It has to be what first? Product first and then a reactant later? Think about that. It's a product of one elementary step and then becomes the reactant of a later step. Where do you think you might find this? Valleys, peaks? Where? In the valleys, yeah. Okay. Think about it, guys. Look at this first elementary step. Isn't this where I would find the products of this step? Isn't that where I would find them? Isn't this also where I would find the reactants of the next step? Yeah. Okay. Transition states. I gave you this vocabulary term because I can't remember which term the AP exam prefers. Transition state, activated complex. They mean the exact same thing. Why we have to have 2 terms for the same thing, I don't know. Okay. Where are the transition states? What is a transition state anyway? Yeah, it's like a hybrid between reactants and products. Where are we going to find those? Yeah, up at the peaks. Okay. Find transition states at our peaks. Okay? So you might be asked to analyze, again, these energy curves are sometimes called energy profiles. Okay? You might be asked to interpret some of these graphs. And the last part of this chapter has to do with catalysis. Catalysts. What does a catalyst do? Speeds up a reaction. Did catalysts get canceled out in our reaction mechanisms? Yeah, they did. Catalysts are not part of the overall reaction. They're not consumed. But they do speed up a reaction, and we'll talk about how that happens. For any of you that go on to take AP Bio with Dr. Fernandez next year, I know a number of you are, okay, or have taken AP Bio, she will sometimes use this word, but most often she's going to use this word, enzyme, okay? An enzyme is a catalyst in a biological setting or a biochemical setting, okay? Enzymes are usually proteins, right? It's just a catalyst in a very specific setting. So go with me on this. Are all enzymes catalysts? Are all catalysts enzymes? No. Okay. There's two types of catalysts out there, ladies and gentlemen, homogeneous and heterogeneous. And I'm going to give you an example of a heterogeneous catalyst that you come across every day in your life. You don't even think about it. There is a part to every automobile, every car, called a catalytic converter. Does anybody know where that is located? It is not under the hood. Where is the catalytic converter on your car? Do you know? You're close. You're getting closer. It's not under the hood. It's not in the gas tank. Keep going back. It's in the exhaust system. It's in your tailpipe. Okay? Your, the output of your engine, okay, is carbon monoxide gas and carbon dioxide gas. Now, we want to minimize how much carbon monoxide, CO, is put out of your tailpipe. And so there's a reaction that goes on in the tailpipe of your car that converts CO to CO2. Your catalytic converter makes this reaction go faster. Do you all know what a catalytic converter is made of? If I tell you they are stolen a lot because they are so valuable, more valuable than gold. Platinum, not diamond. Platinum. They're made of platinum, so they get stolen a lot. In fact, my very first year of teaching here at Oakton, we had 15 or so teachers one afternoon. There must have been some person that just went from car to car to car to car and just took them all away. They did not get mine. I was very fortunate. Okay. You don't want things to happen to your catalytic converter. It's made of platinum. It's very expensive to replace. Okay. But platinum at room temperature is what state of matter, ladies and gentlemen? Solid. Okay. All of the reactants in this process in your tailpipe are gases. A catalytic converter has an example of a heterogeneous catalyst. It's a solid interacting with all gaseous reactants. It's in a different phase. If somehow we could make a gaseous catalyst, then that would be a homogeneous catalyst. Okay? See if you remember this from Chem 1. How does a catalyst make a reaction go faster? What does it do? Ah, very good. It lowers the activation energy. You're exactly right. Okay? It provides a new pathway to get from reactants to products. Okay? Maybe it introduces two elementary steps, two different reactions to get from here to here. But the key is reactions that have lower activation energy. Okay? If you lower the activation energy, then percentage-wise, you're going to have more molecules with that required amount of energy. This is important right here. Delta E, guys, what I mean by delta E is the difference. It's not a very nice E. No, that's terrible. Better. Delta E is the energy difference between your reactants and products. Doesn't matter. Look at the red line, look at the blue line. They start and end in the same place. A catalyst does not affect that. Okay? Now, the last thing that I want to say, guys, is that I want to explain to you how catalysts do this, because I got really frustrated in high school and even college to a certain extent that nobody would ever tell me, how does it do that? How does it lower the activation energy? And I'm coming from a biochem background, okay? So I'm going to explain it with an enzyme. I think you talked about this a little bit in 9th grade biology, but I could be wrong. I'm going to draw something on the board that's going to look like a big letter E. It's not an E. Are you ready? Here we go. Yeah, I know what you're thinking. It looks an awful lot like a big letter E. It's not an E. No, no, no. It's an enzyme, which, yeah, I know starts with the letter E. No. Okay. It's not a big letter E. I'm using this to represent, this is an enzyme. Okay? Enzyme. Okay? And here are my reactants. I'm going to try to draw this as best I can. I am not an artist at all. Okay, there's reactant 1, and reactant 2 kind of looks like that. Can you all see that those two pieces, like puzzle pieces, fit really nicely right there and right there? Can you see that? Okay, I think you do this in biology a little bit. It's like a lock and key mechanism, okay? Enzymes have these pockets, and they're called active sites. And this is why nature is so amazing to me. These enzymes, their pockets are perfectly shaped to fit just that reactant and nothing else. Okay? Do you all see that these two pieces, when they fit in there, they would be right in contact with one another? Do you see that? Okay, and this is perfect. It's on Valentine's Day. Ready? Boy, girl. Matchmaker. Okay? Would these two get together if they were left on their own? They might. But they have a much better chance of becoming a happy couple if we've got this matchmaker bringing them together and saying, hey, come on into my office, step inside here. And then this couple leaves and is this happy couple that rides off into the sunset. Now guys, let's go back to what we talked about. What's required for a reaction to happen? These reactants have to contact each other with a certain amount of energy. Would these two do that if they were left on their own? Yeah, probably. But it'll happen a lot faster if I've got something bringing them in close proximity with each other. Yes, Natty?
Well, just what the enzyme get from it, does it just exist to help reactants bond?
Yes, that is all it does. The enzyme exists to do nothing else but help lonely people become a couple. It doesn't get anything out of it, you're right. And it's not consumed, it's not changed in any way, okay? But that's how that happens. And I think that is just really, really cool, because nobody ever explained that to me. Now, here's the thing though, okay? Do catalysts speed up a reaction? Absolutely they do, but only to a certain extent, a certain point. Because think about it. Now this is a ridiculous situation, but let's say that I have a beaker filled with reactants 1 and 2. Okay, you with me? Beaker full of R1 and R2. And to this beaker, I add one single enzyme. Now that's ridiculous, but just pretend with me, okay? If this enzyme is assisting this couple right here, can this enzyme help any other couples? No, the enzyme is busy. So here's the thing. Once that enzyme is working at capacity, I can add more reactants as much as I want, but that's not going to make the reaction go any faster because this enzyme is working at capacity. Ladies and gentlemen, that is the definition of zero order. Let me show it to you graphically. Okay? To a certain point, a catalyst will make the reaction go faster. Once you reach a certain point, when all of those active sites are filled up and that enzyme is working at capacity, you can keep on adding more reactants, but you're not going to make the rate go any faster. And guys, that is what zero order is. Zero order means adding more concentration of reactant and the rate does not budge. Okay? I mean, if you want another analogy, and this is just fresh on my mind because I was there not too long ago, you're at the DMV, which is, by the way, if you ever have to go to the DMV, it's like entering the seventh circle of hell, okay? I'm just putting that out there, all right? But let's say there's only 2 people working at the counter, and there's 100 people in line. Well, if those 2 people are working with customers, we can add more people to the line. That's not going to make the line move any faster. Especially when you're like me and you get all the way up to the counter and the lady at the counter's like, sorry, honey, I'm going on my smoke break. She's got to have her cigarette before lunch. Anyway, it just drives me nuts. Okay? So think of these as like the lady at the DMV. She's trying her best, and then she has to go on her smoke break, and then she can't. All right? Yeah, I don't know what the equivalent of a smoke break is for the enzyme. I don't know. And that's the end of the chapter, everybody. Woohoo!